Hello, hello. Welcome to our next live stream. How's it going, everybody? Hope you're doing well. We're going to try the first post-Christmas live stream. And we have some exciting news. We're doing a new book today, which should be very fun. So welcome, everybody. I didn't even have this one scheduled, so we might let people file in a little bit before we get going. But we have a new database book that we're going to be talking about. I'm going to check and make sure that this all sounds good. Let me go over here and make sure y'all can hear this well. Yeah, I think this is going well. Good, good. Welcome, everybody. So anyway, we're doing a new book starting today and going into 2026. We're going to be talking about database internals. This is a book by Alex Petrov, and other than I've just started it recently, but I hadn't read it before, and so I'm excited. This is going to be fun. The nice thing about this book that I like so far too is it's easier. I think it's got better sort of bite-sized chunks that we can go over on stream because it's like 14 chapters and it's only 300 pages. I've only read the first little bit, but so far it's very, very good. So we have a good morning. Good morning, Sharik. Kenway says hi. Hello. Sounds good. Hi. Yes. Hello, everyone. Welcome in. So yeah, I didn't even schedule this one. So we'll just chill a little bit here at the beginning. But like I mentioned, for those just coming on, what we're going to start doing is the next book. So we finished designing data intensive applications. Where is that? Oh, it's over in a pile on the floor over there. But we finished that book. And a lot of you, if you've been following, you saw my review of it. You've seen the videos on YouTube. This is streaming live on YouTube and on X and on LinkedIn, I guess, too. But anyway, that was a good book. It was long, but I also see why it's so well regarded. I left some sort of a review, a short review that I posted recently. But I think probably my biggest feedback on it is it's a really, really good book. I did feel like the last couple of chapters started to sort of drag and get a little bit repetitive, and I feel like one chapter would repeat things multiple times. And so I feel like the last couple chapters of the book or second half of the book could have been tightened up by 50 pages or so. It just had some stuff that was sort of excessive. Hello, good morning. But other than that, I think it's an amazing book, and I would recommend really not even just like if you're interested in databases, becoming a database engineer, backend engineer, stuff like that. Yes, definitely read it. But really, I think everyone would benefit from it. Even if you're like mostly a front end guy, right? Like it's becoming more and more where you have to like know little parts of the whole stack. And so knowing about database design decisions and data pipelines and performance, all that is super useful for your career and for building good applications. And then I was thinking of doing this different book, the book called Build an LLM from Scratch, but I kind of changed my mind on that a little bit. I wanted to stick with something more databasey. And this is kind of another very popular book in the databases world. It does have some overlap with designing data intensive applications, which is why I was a little hesitant. But it also has some kind of different things, and it focuses more, like the title suggests, on the internals, particularly the storage layer of a database system. So a lot of the focus of the book is on, B tree structures and LSM tree structures and the trade-offs, and not just those two, but all kinds of other structures and the trade-offs between those, row storage versus column storage, how we do lookups, how we organize data on disk, the advantages and disadvantages of all these different things, and some other internals topics as well. So I think it'll be really fun. And yeah, let's see. Abinash is perfect timing. I'm also learning about Postgres internals. Yeah. So these, designing data intensive applications, database internals, these obviously are not Postgres specific. Each database chooses different things. One of my sort of favorite things to do and to tweet about and all this is comparing the different design choices between Postgres and MySQL. Even though Postgres is very popular and it's a great database, it isn't the best at everything. There are some things that, for example, MySQL, at least in my opinion, makes better trade-offs with or makes better design choices. But at the same time, Postgres development is more active than MySQL development. So maybe over the next couple of years, it will there will be less and less things where we could say, oh, Postgres doesn't do this as good as MySQL. That would at least be the hope, right? As more and more sort of legacy things or whatever get improved and improved about Postgres. So I love Postgres, but I think there's room to improve, as there always is. So yeah, so today we are gonna, I see there's more people filing in, so I'll just say it one more time and then we'll jump into some of the topics. We are gonna go over chapter 1 of this book, and chapter 1 is really mostly an overview. So we're gonna just kind of like touch on a couple of the subjects that I think are interesting from it. But I would recommend, if you're interested in following along with these streams, the plan is to at least once a week, potentially some weeks even twice a week, do a stream where we go over one of the chapters, pick a couple of different subjects to talk about. And then I also actually want to start doing a better job at taking the stuff from the streams and chopping it up into separate YouTube videos, right? Because sometimes I'll talk about something on stream for like 10 minutes and it makes a nice bite-sized chunk where people shouldn't have to scrub through a whole stream just to hear our discussion on, whatever, row storage versus column storage, right? Maybe we talk about that for 15 minutes. That could be its own standalone video that people can share out or watch to learn. So I want to do that too. And the other thing I will say is I love questions. So you should feel free to ask questions. I don't have one of those stream setups right now where you can like see the live chat going, but I can see your chats. And if you're on, X or YouTube, you can see the group chats. So drop comments in there. And then as we're going, I'm occasionally pick a question and pull it up on the screen, and then we go over it and talk about it. So we can do all that kind of stuff. But yeah, great way to kick off the almost new year, learn more about databases. So yeah, like I said, and then I guess the other thing I will say too is, of course, if you want to follow along with these streams, go buy the book. I bought it on Amazon like last week or 2 weeks ago. When was that? I don't know. It was like 10 days ago or something. I bought this and another databases book. So go buy it and read along if you want to kind of get the more full experience of these streams. So yeah, let's see. One of the things that maybe we could talk about, let me switch gears here so that I can manage the stream a little better. Switch to this view here. Okay. I'll put myself over here. All right. So one of the things that, again, a lot of things. This chapter is an introductory chapter. But one of the kind of core components of this whole discussion of what database are you choosing, what database engine are you going to choose, is there's 3 broad categories that databases fall into. And even this doesn't really capture them all. But the 3 broad categories that databases fall into are OLTP, OLAP, and HTAP. And we'll draw boxes here on the screen for each of them. So we've got our OLTP database. Maybe I should zoom in a little bit more here. Go here, do this. Okay. And then OLAP. Some of you probably know what these mean. Some of you don't. And HTAP. And again, sometimes you see in tech or whatever, you see a bunch of 3-letter acronyms and you're like, get me out of here. Why are we using so much jargon and terminology? And sometimes it's like that, true, but then sometimes there is like good use for categorizing things in this way. So I think this is an example of it's useful to categorize things here. So these databases are OLTP, that stands for online transaction processing. And basically what that means is it's kind of optimized for a lot of very small, short transactions where you're reading small amounts of data. And this is the kind of database that powers most applications, right? If you are on Twitter right now, right? Or you're on YouTube or whatever, there's almost always some form of OLTP database. It might be MySQL, it might be Postgres, it might be some, on Google, right? Since Google owns YouTube, it's probably something like Google Spanner that's powering that, or maybe something custom for YouTube. But it's a database that's designed to do things like look up users when they log in, or when you load your profile, load the user preferences, or load the user's, whatever, light mode, dark mode settings, right? All the different things that just you need to be able to fetch about users and about profiles and about accounts when you're interacting with an application. typically get stored in an OLTP database because they're good at storing those, structuring those. Often it's a relational database, but even databases like MongoDB that aren't relational kind of fall into that OLTP category. And they're also good at doing these short, semi-random lookups, right? Where different users are logging in at different times. So you need to be able to arbitrarily fetch information about any user or any account or any video. So we could kind of just start writing a list, right? Like MySQL is in here, Postgres is in here. Let's see, Mongo, technically SQLite, although like SQLite maybe isn't the best for really high scale, but technically it falls into this category here. I'll make this text larger. So like these databases fall nicely into the OLTP category. And again, there are some like proprietary ones like Google Spanner, or there's some other distributed kind of ones. But something like this powers almost every single application you use on the internet. The other category, or the next category, is OLAP. And this, the A there, stands for analytics. So essentially this is, instead of a database designed for inserting lots of small things, fetching lots of small things in a semi-random pattern, it's designed to do analytics on often big data sets, right? So this is like, hey, it's the end of the year. You think about a lot of, I need to drink some water here, but a lot of people do like Spotify Wrapped, right? Or I don't know, what are all these other, like these wrapped things at the end of the year where you can see a summary of like, what were your most listened to artists, or what was your most watched, YouTube channels, like all of these kind of things. So if you think about the information that's displayed in a Spotify Wrapped or a YouTube Wrapped, it's kind of an analysis of an entire year of your specific data set. But still, if you're a heavy user of Spotify or YouTube or whatever, that's like kind of a big chunk of data that it needs to do analysis on to figure out what was Ben's most listened to artist or most watched YouTube channel. But then there's also the bigger picture of just like, as a business, a lot of businesses want to do analytics, not just per user, but like over their whole user base, right? Like what's the average age of our user base so that we can better target that user base? Or what is, what's the average amount of, what time of day do people spend the most time on Twitter or on YouTube, right? Or watching streams. So doing these kind of deeper analytics where you might have to analyze many gigabytes or even many terabytes worth of your users' data to come up with answers like to better run your business, to better help your customers, right? To do reporting at the end of the year and all of this kind of stuff. So although you can run those kind of queries on MySQL and Postgres and Mongo and SQLite, they're not really tailored in terms of how they store the data on disk. By default, they're not really tailored for that kind of stuff, right? So there's different, even within OLAP, there's kind of different subcategories, right? There's like, well, databases that work well for time series analytics, or databases that work more for generic analytics and all this kind of stuff, right? But some examples are things like ClickHouse is a popular one for time series analytics, but also just analytics in general. DuckDB, this is one actually, why can't I spell? Apparently I can't spell. DuckDB, most of you know, I work at PlanetScale, and we recently released an integration with them, and there's the Mother Duck Cloud that you can use with them, right? So things like DuckDB, there's like Timescale, there's a bunch of, again, like proprietary ones like Google, Bigtable. There's a number of these things that are kind of designed for that, right? And even this one here, like Timescale, is actually, I'm going to take this one off the list. I actually haven't used it personally, but that's actually a Postgres integration, or extension, I guess I should say. So there's a lot of these things where Postgres, you can integrate an extension into it to give it additional capabilities, right? To do vector search, to do analytics, to do cron jobs, to do all these different kind of things, right? And that's can be good in some cases and dangerous in some cases if you stuff too many things in one database. But I'm going to focus on just like standalone things. Why did I write Bigtable? Isn't this is Google BigQuery is what it's called, right? I always get BigQuery and Bigtable, but this is like a Google one. Why am I forgetting what Amazon's? I think Amazon's, is it called Redshift? Let's see. Yeah, Redshift is kind of their main one. I always forget. Redshift. So all of these kind of things, right? So these are like standalone either query engines or databases as a whole for doing analytics type stuff. And again, these are not comprehensive lists, right? There's more in this list. There's more in this list. And so these are optimized for those things. And then HTAP is kind of this hybrid, right? There's this sort of idealized goal out there. And I honestly don't really have much experience at all directly using HTAP databases. But there's this idea that maybe you can build databases that take a hybrid approach and do both well. The only one that obviously comes to my mind is like Single Store, which I'm trying to, but I don't think Single Store is an open source product, right? So I might take that one off because I kind of want to focus more on just like, I guess I put some non-open source things too. SAP HANA. Yeah. Okay. Interesting. Yeah. So there's like maybe less good options out there. And I think the other thing too is that the industry, I think, is kind of over the years realized that HTAP is just like not necessarily ideal, right? Especially once you get to, I don't know, put some of these others up on the screen here. But I think something that the industry has kind of learned is this, especially when you're at scale, the idea of just putting everything in a single database and having just this one giant unified place where all your data is. It's a nice idea in theory, but in practice, you run into a bunch of issues with compute competing for each other, or there's a lot of data duplication. So how do you make sure all of the different formats and layouts that you have data stay in sync? So like, obviously there's still people that use these products, but I think generally, if you're at a large enough scale, a better approach is to kind of have separate databases or data pipelines for your OLTP and OLAP. Obviously, there's always exceptions to the rule, right? So we're not going to focus much on this. Obviously, you can combine them together, but the main focus that I'm going to talk about kind of today and probably throughout the rest of thinking about the book is these two, right? OLTP and OLAP, and the trade-offs that you make to optimize between OLTP and OLAP. And we'll look at the possibility and ways in which you can sort of try to combine the two into one thing that works well. So that's the idea of where, what we're going to talk about today and kind of where we're headed. Let's look here. We got an interesting question. So do OLAP databases still use the same data structures in OLTP like B+ trees and LSM trees? Good question. The answer is, again, unless you're doing a hybrid approach, the answer is generally no. And let's talk about that actually. I have that on the list of things I wanted to talk about. There's a lot of nuance to this question because even like within OLTP, there's different ways you can lay data out. Within OLAP, there's different ways you can lay data out. You can have things that kind of borderline and take approaches from both. But the big difference, kind of the general broad way of thinking about the difference is row storage versus column storage. And generally, row-based storage aligns well with OLTP workloads and column-based storage aligns well with OLAP workloads. So let's just, we'll talk about this for a moment and then we'll do some diagramming. So OLTP, if you think about what it's doing, in fact, let me go, I think what I want to do is make a table here. Let's make a table. Oh, you know what? I might have a table I can borrow because I'm in the same, let's look here. Do I have like an example table? Yeah, I think we did this before. Okay. I'm going to take this. Okay. Ooh, kind of messed it up there. Let's move this down. All right. This is looking a little better here. Great. So the question is, what kinds of data structures do we use between OLTP and OLAP databases? And so let's talk about this broad idea of row storage versus column storage. And let's let's see. Oh, Abinash says bye. Good night. Good night, Abinash. Have a good night. So let me go back to here. So the question that we're trying to answer is what kinds of data structures are used between OLTP databases that are doing more transactional processing and analytics databases. And often the simple way to think about this is the difference between row storage and column storage. So to take a look at this, we've got this sample table up here. And what I've got is just like a really basic user table, right? Most applications need something like this, a table that has your usernames, your emails, maybe you store addresses, sign up dates. This one's small. Often you'd have many more columns on a user table. But let's think about how we would lay this out physically on disk to optimize for different circumstances. So we think back to what we talked about before. If you're an application like, let's say you are YouTube. Let's see, let's make a little box here. Oh, we're still red. You're YouTube. And I guess red is fine because YouTube is red. So if we're YouTube and we want to look up extra large text, we want to be looking up, right? A user logs in. Okay, when a user logs in, you're going to make a request to go and look up. Oh, that's not the line that I want. I want this. You're going to make a request. Okay, so Ben logged in, right? So you're going to look up Ben by ID, find Ben's user profile, make sure the password lines up, all that kind of stuff. You might even update some rows, like this has sign up date, but you might also store last logged in date. And so over here, further along, you're updating like when Ben last logged in, these kind of things. And then if I navigate to Ali's profile, the YouTube app might need to go look up Ali's profile row, and then from there find Ali's like homepage row to figure out what banner to display and what profile image to display, right? So essentially, as YouTube is doing things, a lot of the nature of loading a profile and loading a video is find a row in a database and grab a bunch of things from that row and maybe even update some of the things in that row. So when I log in, it needs to fetch my name so that it can display it up in the corner. It needs to update my last logged in date. It needs to grab my ID so that it knows as I make actions, it can store things based on ID there in the future. It needs to load my email so that if I go and look at my profile page, it sees my email there. So I need to do a bunch of stuff that's sort of clustered together by these rows. And because of that, it makes sense for a transactional database like that to store everything that's in one row together. So the way that we do that, we'll just go look at this. I'll copy all of these and we'll kind of just see row storage versus column storage in action over here. So for row-based storage, the way that we're going to lay this all out on disk is essentially by putting all of these things together. I can actually just get rid of these titles here. So let's say I have a file that is storing everything in this users table, right? Literally the first bytes of the file, probably some metadata, but then once we get to the actual table data is the ID 1 as an integer, and then the string Ben, and then the string Ben at hi.com, and then this street address with, delimiters, whatever, and then the date. And then the next byte is this 2, and then the next user and the user's email, right? So we're clustering all of this stuff together based on, right? Like if I'm Ben, I want to put Ben's email nearby. I want to put Ben's address nearby. I want to put Ben's, last or signed up date nearby. So one row, all of the data is near each other on disk, right? And this is what we would call row-based storage. And this is what's used in MySQL and in Postgres and most of these relational databases, because there's kind of this assumption that when you're looking up a row, you might not need everything in that row, but you're probably going to need at least a few bits of other information in that same row. And so we should store it all together. And especially because when you're a hard drive disk, you don't read single integers at a time. But what you're actually doing when you're a hard drive is you read pages, which are often 4 kilobytes or 8 kilobytes or 16 kilobytes. And so a single row often fits in a page. In fact, often multiple rows fit in a page. So if you're going to have to read, Ben out of this row anyway, it's likely that from the hard drive or solid state drive, you're going to have to fetch a 4 kilobyte chunk. So all this other stuff is probably going to come with it anyway. So let's organize the data. Let's leverage that in how we're laying things out on disk. We'll take a quick break to answer this question here. Quick question. Should I start designing data-intensive applications first or database internals first? I would say probably the better thing to do in a vacuum would be to do designing data-intensive applications first, because I think, well, I haven't finished this book yet, but that's probably a better like overall overview versus getting into the specifics of database internals. But given the circumstances, if you want to follow along with these streams, because I'm going to be streaming more on this over the next month or two, you could just skip to database internals. That way you can follow along with what we're doing here. Do DDIA some other time. So it's a good question. All right, let's go back to here. So next, column storage. Let's look at column storage. If you think about doing analytics, actually, I'll just copy this over here. If you think about analytics questions, so things like, what would be an analytics? We talked about some example analytics questions you could ask in general, but given this specific data set, I'm trying to think of what a good question would be. So maybe we want to say, we're doing some business analytics. We're at the end of our year, like we are now. We want to figure out what time of year did most people sign up for new YouTube accounts? Because maybe we can draw some business ideas from this, right? Like maybe most people sign up for YouTube in the summer when they're out of school and they're bored. And so maybe that can lead us to say, hey, we could like advertise more in the summer because we know that's when people are more likely to want to make a new account. Or maybe we're surprised and people sign up mostly during the school semester for students because they're trying to look up videos on how to learn and do well in their classes or whatever, right? So we're trying to figure out, glean some insights for what time of year the most people sign up for new accounts. What we would probably want to do is go to our user table, because that's where we've stored the information about when people create their accounts. And we would want to basically do a big scan over the whole table. And if your YouTube scale, right, you actually have like 2 decades of data and you've got, you know, hundreds of millions or even billions of user accounts. So that's a big table to scan over and get all of this information for. But if I'm just trying to answer that one specific question, I don't actually care what address people live at. I might care about that for a different analytics question, because then my next question might be, well, what parts of the world are most of our user accounts in, right? Or I don't care about their email. Again, you might, for a different analytics question, you might want to know, you know, what are the most popular email domains from 2025 that people use to sign up. But for the question at hand, all you care about really is this column. We want to see this column, and then we basically want to build like a line plot to show what times of year people signed up most. So in this case, I only really care about scanning on this data here, but there's billions of these rows. So it actually, if I had to read, every time I wanted to read Ben's sign up date, if I had to read all of this from disk, and then Zed's sign up date, I had to read all of this from disk, and then Ali's had to read all of this from disk, I would end up doing a lot of IOs that I didn't actually have to do. So the better way to organize this often for analytics queries is to group things together by column. So all the IDs go together. Let's move this over here. So all the IDs go together, and then right after, again, there would be a lot more. We're just doing 3 for as a simple example. And then once I've written all of my IDs in disk, then I have all of my names, and then I have all of my emails together, and then I have all of my addresses together, and then finally I have all of my sign-up dates together. So then, if I wanted to do this analytics query where I was trying to figure out, you know, what times of the year are the most sign-up dates, I could do a big, long sequential scan of contents on my hard drive, but just the section that has all of the dates in it. And then I basically skip having to ever read all of this other stuff. And that's actually only one part of it. So that in itself would give a big advantage. But there's another advantage too that's maybe a little bit more subtle, which is there's only 365 days in a year. but I have a billion users on YouTube. So I have a billion records that the cardinality, the number of different values for, well, I guess technically here we're including the year as well. So, but still over the course of only 2 decades that YouTube has been around, what is that? That's maybe, is that like 10,000 days or something like that? Let's see, 365 times 10 would be 3,600 times 20 would be, let's just say 7,000. So that's like 7,000 days, right? So a billion people, there's only 7,000 possible values. So the other thing that you could end up doing, I'll just copy this down to a new spot down here, is what you actually would end up with if this data is sorted. So this means it assumes it would have to be sorted by date, is you'd end up with a bunch of people that all signed up on 1025, 1025, 1025, 1025. And then we'll just go down to the next line. Then, you'd have a handful of people, maybe there's only 2 this time that signed up on 1026. And then maybe there's 3 more that signed up on 1027, 1027. Oh, wait, that's 26 still. 1027, 1027, 1027, and so on, right? So you actually end up with, and often this is the case when you have analytics data, a bunch of repetitive values. This might not be the case for addresses, right? Like technically you still would probably have some repetition in there because addresses change hands over time or multiple people can live in the same home, but there's going to be less so because there's, millions or billions of different addresses out there, right? But for sign-up dates, there's a lot of repetition. And so what you could actually do is do sort of a compression optimization. And you could use different compression techniques, but like a really basic thing would be, I'm going to plop this down and then I'm just going to say like this, repeated times 4. We should put a space there. So that times 4, and then 1026, how many were there? Times 2, and then 1027, I think there were 3 of those. So times 3, let's get rid of these here. So basically I have both saved disk space, but then also this would facilitate my analytics query running faster because I've kind of already compressed all of this into how many people on 1025-24, how many people on 1026-24, so that the query itself could run faster because it has to do less I/O, and I've kind of already done some like pre-aggregation of the results. So that is kind of one of these fundamental trade-offs, right? If I know my goal is doing lots of analytics, figuring out what day of the year people sign up the most, figuring out what parts of the world, right? I could do analysis on the addresses, figure out what parts of the world are most popular for YouTube watching. And then I could even correlate that to the time of day, right? Like, what's the country watching the most YouTube videos at 11 p.m. UST, right? If I wanted to do analysis on email domains, I could even join across tables and do analysis. Oftentimes, this row-based layout, which works great for just generally powering your application, but it's not necessarily the best for analyzing user patterns and trends and all of this in your app. So this is one of the big reasons why there's a whole separate category of databases that optimize for this kind of work versus optimizing for computing analytics on what you're doing. And there we go. That's the difference between these two. There's a lot more detail into like how these are implemented, and just looking at this is an oversimplification because there's lots of ways that you can optimize this and do this. There's lots of different ways that you can optimize this. There's different trade-offs. And again, there's ways to sort of make a hybrid approach. But this is the basic like trade-off between analytics and OLTP. Hope this is interesting. Haven't had a lot of questions the past few minutes, but if you got them, drop them down. I like to chat. There are a good amount of people watching, which is cool. Yeah. So that's some of the stuff I want to talk about. I've got more. We'll sit here for a second. So let's see. for those that came in late, I'll just remind you what we're doing. We're talking about this book. The first chapter is what I read, and then I'll probably read chapter 2 later this week. And this week I might even do a second stream later in the week. There'll either be 1 or 2 streams a week going forward. And yeah, the intro chapter was mostly just like an overview, right, of the different aspects and the trade-offs of storing data in different formats and different kinds of storage engines. Let's see. Okay, we'll have a look at DuckDB internals. Yeah, I don't know. That's probably something I should look at more. I don't know DuckDB internals super well, but it is a very cool tool. I got to use it a little bit when sort of PlanetScale and DuckDB announced this partnership recently where you can use the DuckDB Postgres extension, but then also offload queries into MotherDuck, which is their like DuckDB cloud. So it's a really cool technology, and I know a little bit about it, but I have a lot more to learn. Yeah. Okay, somebody asks, what's the benefit of dictionary encoding versus run length encoding? Yeah, this is something that the Designing Data Intensive Apps book talks about. I don't know yet if this book kind of gets into that or not, but that has to do with basically different encoding or compression, and I think it's primarily used if you're doing this sort of, oh, you can't see my screen anymore. If you're doing column-based storage, like what we were talking about before here. And I think RLE is pretty popular, but that's not really, unfortunately, my area of expertise. But maybe we'll get to it if the book talks about that more. But I do like talking about database trade-offs. So, okay, let's see. What, yeah. There's a bunch of other places that we could go here. Just trying to think. I took a few notes. Maybe what we'll do, this part was kind of interesting, and I wanted to touch on it a little bit. I'm going to go back to, if you have your books. I feel like I'm back teaching a classroom. I used to be a college instructor. I've just got my virtual little class here. So if you're in the book, it's page 10, but I'll go over here. We'll draw some boxes in a second. But one of the things that the book talks about, database internals, is there's these different components to database storage engines that are all very important. Oops, I just think I just tapped my mic. So for database internals, particularly storage engines, there's different components to the storage engine that all play a different, very important role, but kind of do different things. And not all of it is directly to do with what we were just talking about, right? Like how data is laid out on disk, but other aspects like managing transactions or managing conflict between different transactions, right? Lock management, essentially. So let's talk about those a bit. And we'll draw some more boxes here because the book has some nice categorization of the way that these things kind of fit together. Yeah. So I'll kind of sort of redraw the diagram that the book makes here. Zoom in. So one box, we'll go back to just this here, is your transaction manager. Your transaction manager. I apparently cannot spell very well, nor can I type very well, but that's okay. And what this is doing, right, like a core piece of a relational database is transactions. This is something that was covered a lot in designing data-intensive applications, but basically we want this concept where a given database connection can send a query or a sequence of queries and kind of act as if it's the only thing connecting to the database. So it wants to see a consistent view of all the data on disk and all of the tables without worrying about what else is going on in the database, even though there probably are, tens or hundreds of other transactions going on at the same time. So this is the component that is saying, hey, I'm going to manage and make sure as multiple different transactions or multiple requests come in to this storage layer that I'm trying to manage, I want to make sure that they are, when they enter, they are getting to see, potentially a snapshot of all the data in a consistent state. And also, once this transaction is complete, does it leave the data in a state that is consistent for the future transactions, right? We don't want transactions to leave data corrupt or half written or anything like that. So we have our transaction manager, an important component, and very closely related to that is the lock manager. And these things kind of go hand in hand. You could almost categorize them as the same thing, but they do play different roles. When you are a query, particularly if you're doing reads and writes, you want to be able to look at a table. Like, let's say you are inserting some new rows into a table. I want to be able to insert rows as a query without some other query inserting rows over top of the rows that I just wrote, right? Like maybe multiple transactions are all trying to insert, new rows to a database. How do we make sure that one can insert into a new slot on the hard drive without the other one claiming that same slot and writing over it, right? Or if I want to look at a range of tables, a range of rows within a table, what happens if other transactions are trying to insert rows in the range that I'm looking at? I might want to sort of get a frozen view in time, a lock or a snapshot on those rows so that nothing can happen while I'm doing calculations with it. And some of that's managed through locks, some of that's managed through other multi-version control techniques, but we need some components to be able to manage, right? Like sometimes a certain transaction wants to lay claim to a set of rows because it's making modifications to them, and any other query that wants to change those rows has to wait until the lock is released, right? So we have this component, and then I'm going to go flip my page so I've got this over here. We've got sort of our main access layer. We could almost call this the CRUD layer, but. So the access layer is, we have our data stored on disk in some format, right? Maybe it's column-based storage, maybe it's row-based storage. Maybe we're using a B+ tree, maybe we're using an LSM tree, maybe we're using some other custom format, maybe we have indexes, maybe we don't have indexes. So there's a bunch of data on disk, but every time a query is executing, it shouldn't have to know all of the details of how to manage the data structure and this and that. It should just be able to say, like, a query that's running, I want this row. And so the access layer knows how to go look up this row by ID in the B tree and give it back the information in that row, right? Or I need to do a lookup on this index, and it knows how to go find that index and do the lookup and all this kind of stuff. So basically, this is the layer that internally, not externally, but within the database, is doing sort of the CRUD operations, right? Create, read, update, delete rows, entries, documents in our database. And this is actually, I think, it's not what this whole book is about, but this is what a lot of this database internals book is about, because it's like, what's underneath this layer? Is it a B tree? Is it an LSM tree? What's the data layout on disk? So we've got that. And then I'll actually copy from this one over here. Two other components is our buffer manager, which is super important. We'll talk about that more in a sec. I'm just going to build out the whole diagram here. And then recovery manager. And we'll put this all in a nice little dotted line, and we'll give it a name. And the name is, this is a storage engine. Okay. So the two other components, right? This is the full picture of the main components of most storage engines. The two components we haven't talked about yet. So the buffer manager is important essentially as a performance optimization, right? We could completely ignore any buffering. And by buffering, mostly what I mean here is we read things from our either solid state disk or hard drive disk, right? And we write things out to that hard drive as well. But disk I/O, even on an SSD, is slower than reading and writing from RAM. And so we typically in these databases, even though the databases we're talking about today are not in-memory databases, there are memory-first databases, but we typically want to keep some percentage of our data in memory to make those reads faster. And even writes, we can write to a log, and then we can update the pages in memory, and then we can flush those out at a later time. So there's a whole component of how do we manage which rows or which pages from disk get to stay in memory versus which ones are on disk. And there's a lot of like, it's a cache basically, right? But there's a lot of sort of theory about how do we optimize these things in the best possible way in something like this. And so the buffer manager is the thing that sort of maintains, hey, when I read a page from this access layer, let's store this into memory. Or, hey, I need to read a new page from the access layer, but my buffer in memory is actually full, so I need to kick something out of that. How do I decide what no longer gets to be in memory? I want to make a good choice, because if I kick something out that I need to read again a half a second later, I've kind of done some wasted effort. But if I can kick it out, and if I don't need it for another hour or 5 hours or day, then great, I've made a good choice about which thing to evict. So that's the job of the buffer manager. And then the recovery manager is less about the day-to-day operations, and it's less about performance, and it's more about the reliability side of your database. Relational databases typically run with where they are writing things to a log, right? If you're MySQL, you're writing to the bin log. If you're Postgres, you're writing to the write-ahead log. And then they make updates to pages in the buffer manager, but there can be circumstances where a database might crash or the power goes out on a server, where some data wasn't fully written back to the B tree index or to the main table storage layer. But we have the data in our log. And so anyway, the recovery manager is this whole component that manages, I want to make sure that if I have committed a transaction, if I have told my client or I've told the rest of the database, hey, I've got this data, I'm going to commit it, that I for sure have it on disk. But if there's any issues with it was only partially written to the B tree index or the B tree index wasn't updated, when I crash and then recover, I want to make sure everything gets restored to a consistent state as if a crash had never happened. Because we never want a relational database, ideally, to get into a state where a row is corrupted or things only got halfway written, or a transaction that the application thinks is A-okay and good and saved, right? Especially if you're dealing with like a payment system or something, you wouldn't want someone to make a $10,000 transfer and then the database, the client thinks, oh yeah, the database told me that was saved, but then the database happened to crash right then and forgot about your money transfer, right? So that would be bad. We want to make sure that we are not doing that. So anyway, those are kind of the main components of a storage engine. And throughout the book, we're going to talk more, I assume, about a lot of these here. Again, the focus being the access layer. But this is kind of an interesting thing too, because you look at this, and this is not even the full database. Like, this is a part of it. This is one component of what makes a database special. But on top of the storage layer, you have your, well, I guess if you kind of work the other direction, right? A query comes in, you have your sort of layer that just handles connections in the first place, but then you have your layer that parses the query, figures out all the tokens, makes sure it's syntactically correct, sends back errors if it's not. And then that gets passed into the query optimizer, which looks at all of your tables, all of your indexes, all of the statistics that it has about the data in your tables, and comes up with what's the optimal way to fulfill this query. And so it comes up with a plan for how to execute this. And then that starts getting passed down into the layers that actually handle that algorithm of execution, which then rely on the storage engine, which is this component, to basically get the data that it needs to scan through tables and do lookups and all of that. Let's see. So someone came in a little bit late here. Totally fine. What book are you covering? So we are talking about the next database book in the series. So this is the Database Internals by Alex Petrov, and it's a very good book so far. I've only read chapter 1, but my plan is to do streams kind of like we did for designing data-intensive apps, but for this book instead, going into the new year. So hopefully at least once a week. So if you want to follow along, I've read chapter 1, and if I were you, if you want to follow, I'd read at least one chapter a week. The nice thing is the average chapter length of this book is only like 25 pages, so a little more manageable than DDIA. But I'm going to stream at least once a week, some weeks probably twice a week, and do a chapter about a chapter or stream. Kareem asks, does the recovery manager, let me go back to this view. Does the recovery manager operate asynchronously from the other two components? Not necessarily, because the recovery manager's operation, I guess it depends on what you're asking. The actual act of doing a recovery is generally going to happen not while all the other stuff is happening, right? Imagine your database crashed and left some data in an inconsistent state. The first thing that happens is your database boots back up, and it will have the recovery manager, before it even starts running queries, make sure that the database is as recovered as it can be before it starts fulfilling queries, right? But in terms of the normal operation of a database, the recovery manager in some sense is always operating, because continuously, as you're accepting new writes and inserts and updates to your database, you're going to be writing those to your write-ahead log or your binary log, which is the sort of record of changes made to your database. And that all plays into recovery. So in some sense, it's always running while your database is running, right? During normal operations. So that is a good question, yeah. So the buffer manager, zoom out a little so we can fit this better with questions. So buffer manager works on the buffer pool, which holds frequently accessed pages. Is the page responsible for holding rows in a DB? Yes, exactly, Victor. So I maybe, there's a lot of different levels of background in the stream. So I apologize. Sometimes I might say things that sound a little too basic, and sometimes I might say things that sound a little too advanced. But when you read and write data from a hard drive, that's happening with pages that are often 4 kilobytes or 8 kilobytes or 16 kilobytes. And then frequently, the way databases work is within a single page, you store potentially multiple rows, depending on how big a row is. So I might read one page and that has 10 rows in it. And then the buffer manager is responsible, in some cases, just for directly managing pages. But some buffer managers are actually smarter about not just storing full pages, but storing on the individual row level. So the buffer manager works on the buffer pool, which holds frequently accessed pages. Is that what I just did? Is the page responsible for holding in a DBA? I think I just answered that question. Yeah. Do Cassandra falls under OLAP? I read MongoDB core engine. WiredTiger makes use of both LSM and B trees. Yeah. I wish I knew more about both Cassandra and MongoDB. I have not really ever used Cassandra. I have used some MongoDB, but I just don't know a lot about the internals of it. In terms of like architecture of databases, my main area of expertise, you could say, is MySQL and Postgres, sort of the popular relational databases. But yeah, I have heard some about WiredTiger. There's actually someone who works at PlanetScale that was a product manager at MongoDB for a while, and we've talked some about that. I wish I knew more details, but again, that would be a cool thing to like, sometimes I just read a paper, right? Like I've read the Google Spanner paper, or I've read the Amazon Aurora paper, just so, well, for a number of reasons, but one of the things that it helps with it is allows me to learn the architecture. In those cases, it's like proprietary software, not open source software, but it allows you to learn sort of some of the specifics of like a different architecture. So I should probably do some either paper reading or something more to kind of understand the specifics of the WiredTiger engine, because it does seem like they've put a lot of effort into making that really good. Can you share your thoughts on tuning the worker threads, which actually writes the data to physical disk from the buffer? Faced a lot of problems with MongoDB. That's interesting that you ask. So I have actually in Postgres, not MongoDB, but I've done a bunch of benchmarking on that. Some of it is public. Some of it is not public benchmarking. I'll show you the public stuff. Let's see. So we can go look at this in the tab here. So this is a, let's see. Okay. So this is a blog post that I wrote on benchmarking Postgres, specifically 17 versus 18. And I know there was a question about MongoDB, but we'll talk about this since it's what I'm more familiar with. And the reason why I wrote this blog is because moving to Postgres 18 gave users a bunch more control over how I/O is handled. There used to just be this default way of handling I/O, which currently is called sync. I believe that's what it's called, right? Yeah, so the same behavior as Postgres 17, but Postgres 18 introduced two new methods, either using worker, which has dedicated worker threads for doing I/O, or using IOU ring. And they're going to keep making that better. So I believe the IOU ring technique only actually helps for reads, and they're working on make it work for reads and writes. Hopefully that comes in Postgres 19. But I was interested in answering this question, right? Like there's always all this hype about this new IOU ring methodology. And so I did tons of benchmarks on EC2 instances, but both ones with local SSD, as well as ones with EBS volumes, which are popular to use for databases. And so I have a bunch of data that actually was kind of surprising, right? So this is why it's cool to do actual benchmarks rather than just sort of listen to the hype around what performance improvements there are. Because when I did benchmark it, I got some surprising results that actually IOU ring in many cases was not as good as I would have thought it would have been. That doesn't mean it's bad, but it just means, you know, it's not a total win all of the time, which I kind of thought it would be, right? For certain kinds of workloads. In fact, in my case, pretty much most of the workloads, it was not the better option. It might be better in some cases, and it will probably keep getting better with future versions of Postgres. But like at the moment, it's not necessarily the best option. So I would recommend reading this. I should probably put this in the chat, which I will do in a second. But I did a bunch of benchmarks. Basically, I think I was mostly using TPCC, which is a popular benchmark for these databases, but did both single-threaded, high concurrency, again, instances with different performing remote attached disks as well as a local disk. As pretty obvious going through this article, and this is what we're big fans of at PlanetScale, is like local disks are the best performing, especially for heavy read workloads. So that's the ultimate hack, is just upgrade to local disks rather than using network attached storage. But I wanted to be thorough because there's a lot of databases that also run on network attached storage, right? And so you can kind of see very detailed information about what settings work better in different circumstances. So yeah, and then also included like some of the benchmarking info. The thing that I had mentioned that I have also done some that is not public, which there's not a particular reason I didn't publish it other than it just didn't seem super interesting after I summarized it, is I did some benchmarking specifically in Postgres on the different IO concurrency. There's two parameters that you can set the number of worker threads and background worker threads for IO. And this was just internally, we wanted to answer the question, we as in PlanetScale, what are good default options for this? And you know, obviously there's some things where you can just go look up online or whatever, but in this case, the best answer was let's just try a bunch of stuff. So I tested a bunch of different combinations. Ultimately, the deltas between them weren't as big as I was thinking they would be, but it still was like a cool benchmarking experience. So, good question. Getting nerd sniped by these questions here. Storage engines are interesting. Look at them. RocksDB, Pebble, you start to appreciate the work. Yeah, RocksDB is an interesting one. For those who don't know, that is MySQL has sort of the most popular storage engine for MySQL, which MySQL has this ability to run on different storage engines. The most popular one for your typical average workload, well, maybe I shouldn't even say most popular because RocksDB is very popular, but what's the right way to put this? RocksDB is very popular, but it's more specific because that is LSM based and it's very good for write heavy workloads. I think it's used pretty heavily by companies like Facebook, and I think they did a lot of the development on it. So that's why it's like widely used. But in terms of like the number of different companies using it, InnoDB is probably much more popular. And that's the one that is a B-tree based storage engine that does row based storage. But yeah, there's just like so many different trade-offs and pros and cons. It's cool to study. Postgres has silent failures. What is a good way to handle that? I would need more specifics on that. Any database can potentially fail you in some way, but I'd need a little bit more details on what you're talking about there. I'd love a stream where you demonstrate how you do these benchmarks. It's an art. Yeah, benchmarking is fun. I also have I posted, what was that, maybe last week, about how I want to benchmark all the versions of Postgres from version 8 all the way to 18, which even though that's only 10 numbers, that's actually 20 years of Postgres. Someone actually has done something that I discovered already. Someone named Thomas Vondra, I don't know if I'm saying his name right, but he's one of the Postgres maintainers. He actually did that, and there's a really cool, I didn't get to watch the whole thing, but a talk online where he shows performance changes over 2 decades worth of Postgres, which is really cool. If I do it, I want to do a few things different, but you can look that up. Thomas Vondra's talk. What do you think about file systems? I was actually thinking about this the other day. I haven't done a lot of either studying or benchmarking really specifically on like, you know, it would be cool to see benchmarks where you say, hey, let's run Postgres with the same configuration, but on 4 different underlying file systems to kind of see which types of file systems are, you know, the most advantageous for different types of workloads. And there's probably a little bit of difference you could study there. So just joined after the last stream of DDIA. Okay, yeah, so I'll catch people up another time here. People are coming in and out. So we're starting this book. I am starting this book, and you can join too. Database Internals by Alex Petrov. Read chapter 1 already, and you know the introduction and all that. And so that's some of what we're talking about here today. How long have we been streaming for? I think like an hour, a little over an hour. Yeah. We'll go a little bit more. I've got more things I want to talk about. So keep hanging out. What should we talk about next? Let's pick, I think the 5 parts of the storage system was pretty interesting. Yeah. Maybe what we'll do is talk about the index structures. I guess this will require drawing more diagrams. Let me see if we already have some good diagrams of this. Yeah, that'll be a little bit more challenging. Maybe what we'll do, we'll talk about, there's another concept where, again, trade-offs, it's all trade-offs, right? Let's talk about the yeah. No, let's do the data files versus index files. Okay. So we'll do data files and index files. I'm going to draw some pictures to kind of prep, and you all can watch me excitedly. You can pretend to be excited. So I'll start with grabbing the table that we were already using over here. I can reuse this. It'll be helpful. And we'll just get rid of some of the YouTube. You can keep dropping questions. I'll just draw a little bit, and then we'll talk through some of these trade-offs here. I'm going to build a picture of an index. Okay. Let's make I'm actually going to add one more row to this here. Okay. So then we'll do some indexing here. Let's see. What do I want to index by? Let's see. Yeah, okay. And then finally here, let's do this. Actually, I'll change this picture slightly. We'll make a little bit of an oversimplification here for how a B tree works. A little too simple, but hopefully this isn't too boring. Who am I kidding? It's probably very boring just sitting here watching me draw. Oops. But we're almost there. And we'll do this. Okay, great. So the thing I wanted to talk about is the difference between table storage and index storage. So we'll cover some basics, and then we will talk more about it here. So let me just see if there's any questions that I missed. Oh, there are a few. Kind of niche, but I think a deep dive on implementing graph structures at scale in a relational DB would be very interesting. I have just the thing for you. It's another planet scale blog, so you might think I'm biased, and maybe I am a little, but a very, very good blog post. I'm going to pull up here, and I'll share the link. I'll put the link in the chat, but I'll pull it up briefly. So this here is specifically, so you asked about vector indexes, right? So this is a blog post that is where you asked about graph databases and graph stuff in relational databases. This is specifically about vectors, which isn't the only application for graph stuff, but this is a really good blog post about how some of the engineers at PlanetScale built a pretty sophisticated graph-based vector lookup that works within all of the ACID semantics of MySQL. So there's a lot of other vector databases out there that can do lookups, but one, either they don't work well at scale, or they don't necessarily follow ACID semantics, which makes them a little bit more complicated trying to use with a relational database. And we built something that essentially does both. And it kind of has some cool interactive diagrams, which if you know me, you know I'm into this kind of thing as well. And you can sort of explore how these indexes work in three-dimensional space, which is pretty cool. So I would give that a read when you have the time, if you're interested in that kind of thing. So I'm going to move this over here, and then we'll start talking about this. Let me move that. Just subscribed, found your channel yesterday, quite literally bought this book, Database Internals. Awesome. I don't know if you bought it because of me or not, but I'm glad you can read along, because we're gonna kind of explore some of it together over the next couple of weeks, months. We'll do a bunch of streams on it. Okay, so that's the way to put this here. There's a difference in databases between the data that you store in a table itself, the table storage, and the data that you store in an index. And there's, for one, just kind of some good stuff to establish about how this works, and then also some trade-offs about how you have indexes point into the place where the table data is actually stored. So let's take a look at this. So what I have here, you saw me potentially drawing earlier if you were sticking around. We have some example table data. So this is a sample users table that, most applications need something like this, whether it's in Postgres or MySQL. And then this is not a sort of really realistic looking B tree index, but something along the lines, right? A tree-like index. We're just going to be vague about it. If you want to learn more about B tree indexes, I've actually written blogs on it, a blog on it, but there's lots of other information out there. But essentially, right, when you have a relational database, you store the rows of a table in some file somewhere. And there's different ways of organizing this. Here, I am just showing it as a simple box with a bunch of rows in it. If you are MySQL, the way that this data is stored is actually in a B tree, which is a special kind of tree that is really well optimized for database type applications. Essentially a tree that works well with the semantics of how reads and writes happen on a hard drive. So this is kind of an abstraction. And then in Postgres, it works a little bit differently, where all of the rows are stored basically in just one big tuple file, and it keeps track of which space in that file is available for new tuples or rows to go into. It can also append new tuples to the end of the file. So the exact way it's laid out on disk varies from database to database, but you generally have some file where all of this stuff is well organized. But then indexes are what we use to make a lot of different queries and lookups faster. And indexes, again, are often built with these B-tree structures, but sometimes they're built with hash-based structures. Sometimes there's even specialized like geospatial ones that use R trees or graph-based indexes. But here I'm just showing, like, our example is this is a simple index. Maybe I should just label these things. A tree index here. And this, oh, I guess you need to be able to see that, is our table data, right? Okay, so the interesting thing is, right, like you have a single table, and in MySQL, actually, by default, it builds the table data into a tree that is indexed based on the primary key. So if we say the ID here, it would actually already be indexed on that. So lookups based on ID would already be fast. But if your application needed to do lookups by username, right? If you wanted to say, select all the rows from this table where the username equals Jim, if you don't have an index, it will have to scan through all of the, well, in this case 4, but maybe millions or billions of rows to find all the Jims. Whereas if you have an index, whether that's hash-based or tree-based, it can narrow down the result sets much faster, and therefore that query will run a lot faster on the database. So we often build on a single table, sometimes a single index, but sometimes a single table can have 2 or 3 or 5 or 10 different indexes all on the table on different columns, or you can even have a single index that combines multiple columns into a single index. Because if you know, like, hey, often people are looking up both by like username, but maybe people can have duplicate usernames. So we also want to include email in the index. You can have those in a composite index together. So in this case, I'm only showing 1, but there might be 10 extra indexes with other column information in it. And so one of the things to be careful about is if you have an index, 1 index or 10 indexes, every time you insert something new into here, so I'll extend this out, and let's say a new user just signed up for my app. So we have user 5 named Sam at hey.com. He lives somewhere, and whatever, I guess we have to pick today, right? 12/29/2025. So new user just signed up. If you did not have any other indexes, all you would have to do is write this, right? Once that is written to the table, now everything is up to date. If I have 1 index, I also have to do this additional write to make sure that Sam is now in the index, so that future lookups for, users based on their username will go fast. So I have to basically do multiple writes. This is a concept sometimes called write amplification, if you read about it in database books and stuff. So my writes are amplified where I actually have to basically do 2 things every time I do an insertion. And you could imagine if I have a table that's queried a lot and I have 10 different indexes on it, every time I insert 1 row, or potentially, we'll stick with inserts for now, I might have to also update 10 other places in my index. And this is a place where the whole idea of logging, like write-ahead logs and stuff, help, because you can't actually write the new data to a log and then only do the index and table updates in memory initially, and then later on you can flush those things to disk. So there's like ways to optimize this and make it a little bit more bearable, but ultimately it amplifies your writes, right? And it makes every insertion slower. So this is why indexes are great. But the more indexes you have, they take up more space on disk. So it's a time-space trade-off. This is like the ultimate computer science trade-off that if you've ever studied CS, it's like what's constantly talked about in algorithms is you can often make things faster time-wise if you utilize more space. And if you want to utilize less space in RAM or on disk, you often have to do things more slowly. It's this like perpetual trade-off. So you have that trade-off in itself, right? You can use more space on disk, but it saves you time in queries. But then there's also this problem of the write amplification, right? So this is the balance, and what, a lot of not just designing the databases themselves, but if you are like a DBA or someone who's a performance specialist, right? You might come in to your company or to other companies you're consulting with, and if you're trying to improve their database, you would probably look at what are your tables, what are your indexes, what are the patterns of queries that are running, what are indexes we should add to make queries faster, what are some that we maybe should remove because they're wasting a bunch of disk space, but we don't really use them very often for queries. So there's almost like a whole industry here, but a whole sub area of tech of just like, how do you optimize indexes on a database? Okay, so that's one aspect of it. And then the other aspect, though, that this book talks about as like kind of an interesting trade-off is if I have this index, the idea is, and again, this is not a precise B tree, this is kind of a loose B tree, but if I have this and I'm doing a lookup for user with name Sam, I would come into the root of the tree and then I would go down the route to Sam and I would find, hey, Sam is a username in my database, but now I need to go find the row that corresponds with Sam. So somehow I have to get from my index, which is in a different place on disk right here, back up to here so that I can fetch all of Sam's data, right? His username, date he signed up, all that. So how do I do this? How do I make the link or the reference between the index and the table data? And two different ways are contrasted here. So one is, and we're going to kind of oversimplify it a little bit, but let's I'll zoom out slightly. So one thing we could do is we could save an actual, essentially direct pointer to like the page on disk where this lives, right? I'll just make up a page address. We'll say Sam, this right here, lives at address, we'll do like a hex number, right? E42A or something, right? So what this allows, and then I'll put ones on the other ones as well, right? E527, right? And so on for the other ones. So if we actually stored like, here is exactly where on disk the SAM entry is, once we do this disk lookup, the very next IO operation I can do can be accessing the SAM row and getting that out. Really good for performance there, right? The trade-off is we now have introduced potentially a lot more index maintenance that we have to worry about, because if I ever, let's say I have to update this, and some databases like Postgres, if you update this row, they actually rewrite the row in a whole new location on disk. So now I have to update all of these in every index to the new physical place on disk where it lives, right? So basically the advantage is that performance at index lookup time, but there's this trade-off of now I've introduced all this maintenance for any time that moves to a different spot. Now I have to like change this link, right? The other thing that I could do is whatever the primary key of this table is. If you don't know about primary keys, this might go a little bit over your head, but can't go into all those details now. But like I was talking about in like MySQL, all of this data for a table is actually stored on disk in a B tree that has the key with ID, right? So you can do quick lookups to any row in a B tree based on the ID. So if instead here I stored 5, 4 for Jim, I'll just delete this. We'll just put these all here. 3, 1, and 2. The nice thing about this is generally your primary key for a user, the user ID, probably doesn't change very often, if ever, right? It might never change. So once I've found Sam, I know Sam's user ID is 5. So I have to go do another lookup into the index that's up here, which might require a few IOs, or maybe even just one if some of the B tree is already in memory. So it might make the lookup, the query itself, when I'm trying to look up Sam's information a little bit slower. But the advantage is now if Sam, I have to rewrite this over in the table and put Sam in a new page on disk, the ID is still 5 for Sam. So this lookup in the future, as long as this index is properly maintained, I don't have to go update the other indexes just to make this work. Now, I've oversimplified a little bit because in Postgres, you can have multiple row versions, and sometimes you still have to go update these things, right? There's always, more to the story than you can cover in a short YouTube video or live stream. But that is, one of these trade-offs, right? In the indexes that are pointing back to the main data source itself, there's pros and cons by choosing like direct ways to get to the data versus indirect ways like identifiers. And this is one of the never-ending perpetual trade-offs of designing a database system. So yeah, there you have it. Let's look at a few questions here. Let's see. Can you explain node splits and node merge when we are writing to B-tree? How does the mem table reduces this write amplification? Oh, okay, yeah. So there's a few components to this. If you are just wondering about node splits themselves, like how does a B-tree work, basically, there's a few different things I'll point you at here. So yet again, right, we'll pull up a blog post on this. This is one of the reasons why it's good to someone like me as an educator to write this stuff down, because it makes it where if someone asks a question, I can just point them at a resource. So I wrote this interactive article on B-trees, and you can look at like how insertions work and when splits happen, and there's even different trade-offs for what size or what percentage full you do splits at. There's all kinds of interesting stuff you can study about the trade-offs of when you do splits and how big you size nodes for B-trees. So I'd recommend coming and looking at this if you're watching and you just need an overview of B-trees and how they work. This also, there's actually a standalone app for this called b+tree.app, a domain that I own, where you can basically just play around as a playground, right? Let's see, add a bunch of things to this B-tree. And so this is essentially just a standalone app for the thing that I built for that blog post over there, right? You can simulate searches and all that. But I think maybe the question that you were more getting at is, let me go back so I can see the stream here. How do you reduce the write amplification? And again, one of the big advantages, or one of the things that you can do, which we didn't kind of do some detailed diagramming of today, maybe in a different stream we can, is this idea of the log. So if you are doing write-ahead logging, this can save you a lot of IO up front, because you can basically, when you insert a row, you can write into one place. All of the other B-tree structures and node splits and stuff you can do in memory and just flush those to disk later on. But again, you're basically just pushing more work till later. But if you have lots of indexes that duplicate data, there sort of is this inherent write amplification that you have to figure out if it's worth it or not for app performance. Understood. Design data intensive applications through your videos. Thank you. That's awesome. Hello. Merry Christmas. Merry Christmas to you. Good idea to make a stream. Go back to here. Talking about 1NF, 2NF, 3NF, BCNF, 5NF, and very important topic about databases. A lot of people don't know. Yeah, somebody asked me a question about 3NF the other day, and I had to go remind myself what the acronym meant, because that's very important. It's also a little bit more on the theoretical side of the design of databases. I took a design of databases class in college and actually one in grad school, but the undergrad version of the class, kind of funnily, was extremely theoretical. It was not very practical other than a few parts of the course. And it was mostly about relational algebra and tuple calculus and all of the different math and theory behind just the structure of data and designing schemas and all that, which is very good. But I also don't really use any of that math anymore. The grad course was a little bit more implementation. So actually implementing components of a DBMS. Connect with you. Okay. Oh, great. Cool. Yeah. You should connect. So for anyone watching, you're welcome to send me DMs on, if you're watching from LinkedIn or if you're watching from X, you can send me DMs if you have questions, but you don't want them to be on the stream or something. All right. Well, I think that was a really good stream. A lot of great questions. I appreciate you all being here, and I will leave you with the parting note of, remember, if you came in late, what we did today was go over some of the topics from chapter 1 of designing data intensive applications. Let's put it up here so y'all can see it well. Oh, camera stuff. Anyway, so this is what we were talking about today, some of the stuff from chapter 1. I'll try and do another stream maybe even later this week or next week. And the goal is, some of you, if you want, you can buy this book and you can read along. You can also just pop in and hang out and ask questions and learn about databases. And then I'm also going to try to clip some of this for some standalone YouTube videos that make it a little bit easier for people to just grab certain parts and watch it and share. So thank you everyone for watching. I will see you in the next stream. See you in the new year.